Thank you very much, Clay. I'd like to thank you guys for attending this webinar. The title of this webinar is Propane Refrigeration, focusing on minimizing power requirements for Greenfield project and how economizer work. Brief introduction of myself. I did all my university education at Oklahoma State University in Stillwater, Oklahoma during the 70s. So you can guess how old I am. In my previous life, I was professor of chemical engineering at various universities. Currently, I'm senior instructor and consultant with over 40 years of experience in oil and gas industry as well as in academia. Worked, as I mentioned, at several different universities, held various academic and management roles and engineering consultancy across upstream and downstream. And I've been lucky to publish more than 110 papers with the help of my graduate and undergraduate students, and published more than 100 tip of the month, we call them totem, and they're posted on our company website. They're becoming very popular in industry. So I'd suggest you take a look at some of these tip of the month, and some of them related to today's topic as well. If you're interested, let me or Clay know. We provide you with information how to get access to the tip of the month. It's free of the charge. I'm experienced trainer specializing in oil and gas processing subjects, senior member of the AICHE and a member of the GPA Research Committee Subgroup 2. Since 2005, I've been full-time instructor for John M. Campbell Company, and end of 2013, Campbell was acquired by PetroSkills, and I'm happy to be full-time instructor or employee of PetroSkills since 2014. The photos you see, some of the, let me explain a couple of them. This is my first virtual G4 I did a couple of months ago. So it's a very popular course. If you're in gas processing, it's some course that you may be interested to enroll. We have several different instructors teaching that course, and currently Kindra, my colleague, is teaching one of the sessions. And this photo that you see here on the right-hand side is in my last G4 face-to-face I did in PAD in Houston with more than 25 participants. Now let's get to the main topic. Here's the learning objective for this webinar, explaining how an available cool process stream reduces power requirements. The second one, using an economizer. So we're going to describe how a flash economizer works when we have two stages of compression. Let me stop this. Okay. And finally, the last option, we're going to explain how a heat exchanger economizer works. So mechanical refrigeration has several applications in industry. Here's an example of a list of example list. We can use them for processing natural gas to meet contractual specification. Example would be meeting hydrocarbon dew points and processing natural gas to recover NGL. The focus here is in deep NG recovery, such as ethane pluses, C2 pluses, and cooling medium for reflux condenser, such as a de-ethanizer and demethanizer, again in deep NG recovery. NG product storage and transportation, making sure the product is stayed in the liquid phase, so we have to apply refrigeration. And finally, the last one, pre-cooling in LNG production. That's a good example of mechanical refrigeration. So let's discuss or explain this process flow diagram, which is for a mechanical refrigeration plant with MEG injection to inhibit hydrate formation. This is for a rich, wet inlet gas. By rich, I mean containing good amount of NGL, and wet, I'm referring to being saturated with water vapor. So the objective is to take the feed gas with known temperature, pressure, and composition and flow rate, cool it down, remove the heavy components from this natural gas to meet a sales gas dew point temperature of 5 degrees Fahrenheit or minus 15 degrees Celsius at a pressure of, say, 7,500 kilopascal or 1,088 psi. To achieve this, I'm going to set my feed cold separator temperature to minus 15 degrees C at 5 degrees Fahrenheit. For sake of simplicity, I'm going to assume it's a constant pressure process. In real world, from the inlet to the outlet of the plant, we have about 50 psi pressure drop. So let's assume constant pressure drop. Ignore pressure drop for time being. If I set the feed gas to this cold three-phase separator, the residue gas coming out of the separator would be the same temperature. So this 5 degree F would be my dew point of my sales gas, which is the same as the temperature of this gas coming out. So the dew point and temperature is the same, assuming there is no liquid carryover in this separator. So I have a good mist extractor here to minimize or reduce the liquid carryover. Now, to see how much heat I can remove by this gas-gas exchanger. By the way, the purpose of this gas-gas exchanger here is to reduce the chiller duty, which is expensive, and I would focus on my discussion today. So to determine how much heat I can remove from process gas in this gas exchanger, I'm going to assume an approach temperature of about 9 degrees Fahrenheit, which establishes the temperature here to be 45 degrees Fahrenheit, 7 degrees C. The approach temperature of 9 degrees means subtracting from 54, 9 degrees Fahrenheit, and I end up with 45 degrees. And this approach temperature has economic impact on my process. So let's follow the process flow diagram, then I focus on the mechanical refrigeration part. So the gas, I put in the tubing of the shell and tube heat exchanger, and I know I'm going to go below the hydrate formation temperature, so I'm going to inject glycol, ethylene glycol, or MEG as European, the rest of the world may call it, and I'm making sure the hydrate inhibitor goes through every tube. And by the time I get out of here, my temperature is cooled down. The process gas temperature cooled down to minus 8.8 degrees Celsius or 15.9 degrees Fahrenheit. So if the shale gas is the cooling media and it's on the shell side, but the process gas was inside, so I come out here, three-phase. I got gas phase, liquid hydrocarbon, and aqueous phase, which is glycol and water. So this is a pre-cooling upstream of the chiller. And you'll see that this gas exchange is going to remove a good portion of total heat removal from the process gas. So I enter the chiller, again in tube side, the kettle type reboiler. I send it inside the tube. The process gas goes inside the tube. At the same time, I inject glycol again to prevent hydrate formation because I'm way below the hydrate formation temperature of my gas. And the tube bundle is immersed in the pool of liquid propane, which is vaporizing on the shell side and removing the heat from the process gas. So by the time I get out of the chiller, I got the right temperature of 5 degrees Fahrenheit, three-phase. I go to the three-phase separator. I separate NGL, which goes to the stabilizer. Aqueous phase going to the, which is rich glycol solution. going to regeneration system on the right-hand side, regenerate and cool it down and back use it again. And the residue gas or sales gas is cold temperature. As I mentioned, I'm going to use it for cool the incoming process gas and leave the system at temperature of 45 degrees Fahrenheit. So in addition to determining by this process, I can determine the gas-gas exchange duty, which is listed here for the condition I mentioned, and also determine on the process side the chiller duty, which is the feed to my mechanical refrigeration system. So let's go back and see how we handle the mechanical refrigeration system. But before I go there, the liquid saturated liquid propane go inside this LCV valve, liquid level control valve, which acts as an expansion valve as well, reduce the pressure. The saturated liquid become two-phase mixture of liquid and gas entering the chiller, and the liquid part vaporizes, removing the heat from process gas. So here it shows the impact of the selection of the approach temperature. If I choose approach temperature of 9 degrees Fahrenheit, my gas-gas exchanger would remove 19.42 million BTU per hour, and the heat duty of the chiller would be 7 million, and the total heat removal would be 26.44. But if I use a lower approach temperature, I remove more heat in gas-gas exchanger. Let's see duty for the chiller. Still, my total heat removal would be the same. So this is one of the tuning key performance variable that we can utilize to lower the chiller duty. Because if we lower the chiller duty, the power requirement will go down as well. The second lower table is the same information in SI units. So the takeaway from this discussion so far is these two key layering points: an upstream gas-gas exchanger, or sometimes we may also use gas-liquid exchanger, may reduce the chiller duty. And also an optimal temperature approach reduces chiller duty, and consequently could add compressor power goes down, which we'll see shortly. So even though the chiller duty is 7 million, I'm going to use the design value of 8.1 million BTU per hour, or 2.4 megawatt for the rest of calculation as we proceed. So this is a flow sheet or process flow diagram for a mechanical refrigeration system, simple one. This is the chiller that we discussed, process gas coming in the temperature, after temperature, chiller duty. Now I have to set the temperature here for the refrigerant, which is propane. Propane saturated vapor coming out. So again, here I'm going to select an approach temperature of 5 degrees C or 9 degrees Fahrenheit, because I want my cooling process cool temperature with 5 degrees Fahrenheit. With 9 degree approach temperature, the refrigerant should vaporize at -4 degrees Fahrenheit or -20 degrees C. 9 degrees Fahrenheit approach temperature is 5 degrees C, so -15 -5 makes it -20. Again, what's the impact of this approach temperature here? If I use a lower approach temperature, my chiller temperature would be higher, and my compressor power going to be less. So here's another point that we can utilize approach temperature to minimize the power requirement of my compressor here. But keep in mind, when we go to low approach temperature, we have to make sure we choose the right type of heat exchanger. And each type of heat exchanger has some limitation on the minimum approach temperature. So now let's discuss different items. Another item that I need to size my simple refrigeration system is condensing temperature in the cooler here. Condensing temperature sets the discharge pressure. If I know discharge pressure of my compressor, if I know the delta P in my condenser. The condenser could be aerial cooler, could be water cooler, or could be cool process gas stream. So the temperature of condensing temperature is set by the cooling media temperature, again applying approach temperature. But before I go to much more detail, let's explain different type of equipment we utilize and see the actual photo, and we proceed as complete this section. So one of the important equipment is this LCV level control valve or expansion valve. Normally it's a V-valve control valve used for refrigerant level control, but at the inlet the pressure is high, which is dictated by condensing temperature. For our case, about 200 psi, and liquid fraction is 1, vapor fraction is 0. As we cool down or as we reduce the pressure, because the chiller pressure, as you can see here, is low, and chiller pressure is dictated by chiller temperature. There is a direct relationship between temperature and pressure for pure component. So we drop the pressure from 200 psi to say 36 psi. Temperature goes down to -4 degrees Fahrenheit as we desire. But look at the liquid fraction. At the inlet, liquid fraction is 1, but at the output of the valve is only 59% and 41% vapor. So the feed to the chiller would be a low pressure of mixture of liquid and vapor propane, and majority liquid. The important item is the vapor part entering the chiller does not remove any heat at all. So not only doesn't help, it also increases my power requirement for compression. So one of the tuning parameters I'm going to play with is to reduce the vapor fraction. The smaller the vapor fraction, the less mass flow rate through here, mass of vaporization, therefore my power requirement for compressor would be less. So this is one thing that we're going to focus as we go along. The next item of importance in this process is chiller. As you see here is the kettle type boiler and propane, liquid propane vaporizes on the shell side outside the tube bundle, removing heat from the process gas. So the propane leaves as saturated vapor at temperature of -4 degrees Fahrenheit and 36 psi. From here we go to the scrubber. The purpose of the scrubber is to prevent any liquid carryover to the compressor, so the compressor doesn't get damaged. And the compressor could be reciprocating compressor, could be centrifugal, could be package screw compressor mounted like this one above the discharge oil coalescer. This is the discharge coalescer, this is the compressor, and the driver on this side. So our objective is to minimize the power requirement of the compressor, because this is the most expensive equipment in this process, and high capex as well as high opex compared to the other part of the process. And finally, the last item for this process is a condenser. The refrigerant condenser could be aerial cooler, as you see here, or could be shell and tube exchanger using water or process fluid, or could be compact heat exchanger as well. So let's review some of the key performance parameters for minimizing power requirement. Chiller duty. As chiller duty, as we saw, is set by the process demand, process temperature, as well as gas or gas liquid heat exchanger that we utilize to minimize the power duty of the chiller. The next item of importance is chiller temperature or pressure. Again, this is set by process gas temperature and chiller temperature approach. This is the chiller approach in the process gas and the propane refrigeration system. Condenser temperature or pressure. This is set by cooling media temperature and condenser temperature approach. Again, the lower approach temperature, the lower discharge pressure, the lower condensing temperature, the lower discharge pressure, and the less power requirement. Fraction of liquid entering the chiller, that's an important parameter. The smaller fraction of the gas or the bigger fraction of liquid, the lower mass flow rate and less power requirement. So the higher the liquid fraction, the better it is because mass flow rate goes down. Of course, we discussed different parameters affecting mass flow rate. We want mass flow rate to be as low as possible to minimize the power requirement for compressor. There are other secondary parameters that influence power requirement of compressor, and that's composition of refrigerant, any impurities, especially light component that impact or heavy component impact the compressor power requirement. And some of the contaminant may get in the system through leakage, and the non-condensable increases the condenser pressure and increases the power requirement. So condenser and chiller fouling again causes the power requirement to go up. Just to refresh, see how the different parameters affect the power requirement. What I'm listed here is the isentropic head. Isentropic head, you can think of it as energy per unit mass, like kilojoule per kilogram or BTU per pound mass, that we have to add to the gas to raise the pressure up. Isentropic here is assuming reversible adiabatic process. We call it isentropic process. In thermodynamics, it means constant entropy process. In real world, meaning 100% efficient. Do we have 100% efficient? Not really, only in our dream. But we utilize this ideal process and to determine the head, and then we will multiply head by mass flow rate, divide by efficiency of process, and divide by conversion factor, we get the actual power requirement for our compressor. Of course, I'm talking about thermodynamic power. If you want mechanical power, then we have to apply the mechanical efficiency as well to determine the driver of the power of the driver. So as you see, the important parameter here is the suction temperature T1. The lower the T1, the better for the power requirement. Discharge pressure and suction pressure of compressor play an important role on compressor power requirement. K is defined as CP over CV here. Heat capacity at constant pressure divided by heat capacity at constant volume. For propane, the range of K is the range of 1.1 to 1.2. So if I say by increasing temperature, condenser pressure goes up, therefore discharge pressure goes up. You can see here how it impacts the head, and if the head goes up, then the power requirement goes up. Just to relate the effect of different parameters on power requirement of compressor. So to perform calculation and evaluate the process, I'm going to explain 3 different methods. We can use pressure enthalpy diagram, or we can use computer program, such as process simulator like HiSys Unisim, Promax, Aspen, VMG, and so on. But for webinar, I'm going to use GCAP, which is our own in-house software. We use it in our gas conditioning and processing courses. And also, I can use simplified correlation from our operator training manuals, demonstrate how they all can be used to aid us with the calculation. So this is a simplified pH diagram. On the vertical axis, I have pressure, and the horizontal axis is my enthalpy, BTU per pound mass or kilojoule per kilogram. Pressure could be PSI, PSIA, or kilopascal. I have different color lines. First of all, this blue curve, this is saturated liquid curve, extend up to this point, which is the critical point, and then greenish color curve is saturated vapor curve. This is for pure propane or pure component like methane, ethane, propane, and so on. The orange color are isotherms, and during the phase change, the temperature remains the same, and we see temperature, constant temperature extending all the way down to the gas phase. These are higher temperature compared to the lower temperature here. And in addition, we have the greenish color is a constant entropy line, or isentropic path, we call it. So let's see how we can use pH diagram to determine to size our equipment. When we enter the expansion valve, we have saturated liquid with known temperature. So if I know temperature, I draw a horizontal line, identifying my known temperature. Oops, press the wrong key. So if I extend this, this is my condenser temperature. Suppose this is 104 degrees Fahrenheit. And I can read the pressure on the y-axis, which is about 200 psi. Of course, the pH diagram I'm going to use for calculation, it's got all the actual numbers on both axes and on temperatures as well. So saturated liquid, I'm entering the JT valve, expansion valve. In JT valve, enthalpy remains the same. So with constant enthalpy, I go down. How far should I go down till I reach the chiller temperature? So I know my chiller temperature of -4 degrees Fahrenheit. I draw horizontal line and extend it here, and I can read the pressure on the y-axis to be about 36 psi. So I'm in the chiller, I'm in two phase. Any point within the phase envelope here is two phase. So I'm entering the chiller, I enter the valve, saturated liquid, I'm getting out of the valve and entering the chiller two phase. This liquid, this line represents the fraction of liquid, and this segment represents the fraction of vapor. So the further point be to the left, the better would be the higher fraction of liquid and less vapor. So when I get out of the chiller, I mean the propane get out of the chiller is all the vapor, it's going to be saturated vapor at point C. And from point C to point D, I'm going through compression. I'm going to follow constant entropy line. So I can do the calculation very easily. So I can read the enthalpy at point B and point C. I know my chiller duty. So if I divide chiller duty, as you can see here, mass flow rate through this system is closed loop, so mass flow rate is the same throughout every component. It's Q of the chiller divided by HC minus HB, which is the enthalpy change. That gives the mass flow rate through the system. Then the power requirement is mass flow rate, HD, enthalpy at point D, isentropic, HD minus HC, and then to make it actual, I divide it by efficiency of my compressor, which I get it from the vendor. So that gives me my actual power. The condenser duty calculation is easiest. This is a closed loop system. Suppose it's my loop. Closed loop, I add any heat of process gas to the system. I add energy to compress the gas. Now I have to remove the heat from the condenser. So energy in, which is the sum of compressor and chiller energy I'm putting in, must be energy out, which I remove heat through the condenser out of the system. So condenser duty in absolute form, so I don't goof up in terms of tracking of the sign. So absolute value of condenser duty is equal to absolute value of the chiller duty plus absolute value of the compressor power requirement. That gives me condenser duty. And I can calculate the actual discharge temperature if I want to by calculating HT actual using this equation. I know all the terms on the right-hand side. So I get HT actual, I know discharge pressure or condensing pressure, so I can determine the actual discharge temperature as well. So very useful, very easy to do, but easier than that is using computer program. The bad thing about computer program is a black box. You don't know what's happening. You have to trust the programmer done the calculation correctly for you. Of course, you have to put in the right information. So this is a screenshot of GCAP that I used to perform the calculation. The blue numbers are the input data I put in. So the chiller temperature -4, condenser temperature 104 degrees Fahrenheit, chiller duty, design value 8.1 million, compressor efficiency 75%, this isentropic efficiency. I said overall. If it's overall, then we get you the mechanical power requirement. The pressure drop in condenser, I assume 6 psi. No pressure drop in the suction side. And as you can see, the program calculated the chiller temp, compressor suction pressure, which is a chiller pressure. And by the way, the software uses the equation I say to calculate these properties and vapor pressure and so on. So I have everything. Let's focus on the key item. The compressor power duty is power requirement is 1,533 horsepower. My condensing pressure is almost 202 psia. The condenser duty is 12 million BTU per hour, and chiller pressure 35.65, almost 36 psia. Mass fluid 21 pound mass 0.8, and fraction of liquid 0.59. So it takes only 1 minute to do it by computer program. Now let's see the concept as well. The chiller temperature is -20 degrees Celsius or -4 degrees Fahrenheit. So we identify that, we draw a vertical line, and we can read the chiller pressure at this temperature. On the left-hand side is kilopascal. On the right-hand side is FPS unit. So this matches with the computer result of 36 psia at the temperature, chiller temperature -4 degrees Fahrenheit. We know the condensing temperature of condenser. So let's identify that 40 degrees C or 104, and then we can read the vapor pressure of propane, 200 psi on the right-hand side, and the left-hand side 1400 kilopascal. So if I know the pressure drop here, say my pressure drop is 6 psi, knowing the condensing pressure of 200 or 201, we add 6 psi to it, and we get the pressure for discharge of the compressor. So the key learning point is the discharge pressure of compressor is set by condensing temperature as well as the pressure drop, and I should say approach temperature as well. The suction pressure of the compressor is set by the chiller temperature. And there is a direct relationship between temperature and pressure for pure component, as you see here for propane. So now the question is, if the temperature of the process gas leaving the chiller, this process gas coming in, leaving the chiller, begins to increase, what action would you take if you are operating a system? So process gas temperature start increasing. You want to take a corrective action to bring back this temperature to the set point of 5 degrees Fahrenheit. If I lower the chiller pressure, would that help? Based on this diagram, it does. Because if I lower the pressure, say from 36, say if I lower it to say this value here, then I can, if I lower it that low value, it's less than -40, that's not possible. So hopefully I can lower the pressure from say 36 to say 30, and 30 give me a lower temperature of say -28 or so. So if my process gas temperature goes up, the way to correct it is to lower the pressure of the chiller, for example. We can determine the power requirement for this compressor using this chart, which is from our operator training manual. This is for simple refrigeration system with single stage of compression. All I have to know is the condensing temperature, so 104 degrees Fahrenheit, and the chiller temperature, which I already know. My chiller temperature is -4 degrees Fahrenheit. So the intersection of chiller temperature and condensing temperature, I read the power requirement, which is about 183 horsepower per million BTU of chiller duty. So my chiller duty is 8.1 million multiplied by 183. This chart is based on compressor efficiency of 80%, but my process efficiency is I use 75%, so I adjust the power requirement would be 1,581 horsepower, and I'm compared to the GCAP, and not perfect match, but very good close agreement, very close agreement. And if I have the compressor power requirement, I can add chiller duty to it to get the condenser duty as well. So if I do the condenser duty calculation, the chart gives me 12.12 million BTU per hour, and GCAP gave me 12.04 million BTU per hour. So very easy. You don't have to understand computer program, and very easily you can use this. And I personally like graphical solution much better because you understand the concept better, and it's much easier to follow as well. So we're done with this. Let's move on. So here, this diagram, I put the numbers with the equipment so you can follow, like the power requirement for compressor, 1,533, and so on. Now, let's see how we can reduce the power requirement. What happens if I lower, what happens to the compressor power if only the condenser temperature goes down? If the condenser temperature goes down, the condensing pressure goes down, the discharge pressure goes down, so the power requirement goes down. So let's use this criteria. Remember, I had a residue gas from the dew point control, and this residue gas going to compressor. Again, typically go to compressor, and compress, and then from there go to gas pipeline. But this is from offshore platform production. The environment temperature is cold enough, so we can use this as a cooling media for the condenser of my simple refrigeration plant. So instead of air or water, I'm going to use this cold process gas, which is available as my cooling medium for condenser of my simple refrigeration plant. So let's see how much power requirement for compressor goes down. I can use pH diagram. This is the actual pH diagram. So my condensing temperature is 54 degrees Fahrenheit, and my chiller temperature is -4 degrees Fahrenheit as before. My chiller duty is the same as before, 8.1 million as well. So I draw a horizontal line. This is 60, this is 40 degrees Fahrenheit, this is 54, and I can read the condensing pressure about 100 psi. So that's the condenser, and point A is saturated liquid out of the condenser entering the JT valve. Now chiller temperature is -4. That's our set point. Now from A to B, I'm going to go vertical because delta H equals 0 for a JT valve. And that gives me point B. And also I can read the enthalpy at point B. And then the chiller, I'm the chiller, two-phase, point B is two-phase. I'm within the phase envelope. Within the phase envelope. This is my saturated vapor chiller. And point C is at the outlet of the chiller, which is saturated vapor. And I can read the enthalpy of this point as well. Then I go to compress into the compressor, compress the gas. I follow isentropic path. This dashed red line, almost red line or brownish color, is my constant entropy lines. I don't care what the number is. I just follow one of them. So I start from here and follow one of them. If I don't have the line at desired point, I keep equal distance between, not equal distance, this appropriate distance between the two constant entropy lines. One of them, here's one of them, and I follow the path, maintaining the course till I hit this discharge pressure of the condenser. Discharge pressure of condenser. Actually, I should go up all the way to the discharge pressure of compressor, but pressure drop is only 6 psi. It's difficult to see on the graph. So now I have enthalpy at the inlet of compressor. I have enthalpy at the outlet of compressor, which I read from the chart. And I can solve, because I know the chiller duty, I know the enthalpy change, I get the mass flow rate. I know the enthalpy change. I know the mass flow rate. I know the efficiency of compressor. I calculate the power requirement as well. So the rest of calculation is the same as we discussed already. And this is the fraction of vapor. This is the fraction of liquid. So because the fraction of liquid is much more, mass flow rate is small, let's go make comparison with and this equation I can use to determine the fraction of liquid. Fraction of liquid is enthalpy at this point, which we call H of F, minus H of L. This is H of liquid, divided by H of V, as saturated vapor, minus H of L. This gives me the fraction of liquid. Or I can measure this distance by ruler, divided by total distance from here to here. That gives me the fraction of liquid as well. Either I can use enthalpy value or I can measure the length of the red segment, divide that by the total segment from saturated vapor to saturated liquid. That gives me a fraction of liquid. Anyway, by lowering the condensing temperature, we increase the fraction of liquid, and therefore the mass flow rate goes down and the power requirement goes down. This is the SI, same, so I'm going to go fast. You guys have a copy of the presentation, so SI friend can have these slides as well. Again, just comparison. If the condensing temperature was 104 degrees Fahrenheit, mass flow rate was 21.8 pound mass per second, but with using the cool process, my mass flow rate went down to 16.2 pound mass per second, and the power requirement also went down from 1,533 to only 723 horsepower. I'm going to skip the rest of it because I have a summary table to save some time. Going to pass through. So we covered simple refrigeration system. We covered using a available cool process to lower the power requirement. And now let's see how economizer with flash tank and two-stage of compressor works and how much power saving we gain by doing this. So what we have, we add one additional expansion valve. Originally we had an expansion valve upstream of the chiller, still we have it. So we add this expansion valve, a separator, additional separator, plus one more stage of compression. And our desired or objective is the same thing: remove 8.1 million BTU per hour heat from process gas at the chiller temperature of -4 degrees Fahrenheit. So my chiller temperature and chiller pressure would be the same as before. My condensing temperature would be the same as before. Simple refrigeration system would use 104 degrees Fahrenheit, and discharge pressure would be of the second stage would be the same as before. The suction pressure of the first stage would be the same as before. Discharge pressure of compressor of the second stage would be the same as before. So at point A on the process entering the first stage valve, I'm saturated liquid. So I know this condensing temperature, and therefore I draw it. I know the chiller temperature, I draw a horizontal line. But this pressure in the middle, this is the interstage pressure here, which is the same as here, which is the same as here, same as here as well. Normally, with computer simulation, we determine this so the power for first stage and second stage become equal. If you do that, the total power requirement become minimized. For hand calculation, I can take this discharge pressure, which I know, multiplied by suction pressure of this first stage, take the square root of it. That gives me a value for interstage pressure. By doing this, I get equal compression ratio for a stage 1 and a stage 2. And the power requirement is close to minimum. Not exact minimum, but very close to minimum. So for hand calculation, I would prefer to do that. Take the pressure here, take the pressure here, multiply them together, take the square root, and that gives me intermediate pressure. For our case, the pressure here about 206 psi for compressor. For chiller, about 36. If I multiply them together, take the square root, probably would be 86 psi intermediate pressure. So intermediate pressure sets the pressure at the outlet of my first expansion valve. So I start at point A, which is saturated liquid, I go all the way down to interstage pressure in this valve here, and then go to the separator, the liquid, which is point E, going to the second expansion valve, and dropping the pressure from interstage pressure to the chiller pressure, which is point B before entering the chiller. In the chiller, I go from point B to C, and then I go to compression of first stage from C to G. Then I do mixing with the outputs of this vapor coming from the separator, which is cooler, add it to the discharge of compressor, which is warmer, and then go to the second stage of compression. And then for second stage of compression, I go from point F to point D. So again, from similar to previous case, I know the chiller duty, I know HP minus HC or HC minus HP. I get the mass flow rate, I calculate power requirement for this first stage, and I can determine the mass flow rate through the second stage, which is higher. The calculation is nasty, so I'm going to do it by computer, even though I can provide all the equation needed to do the hand calculation as well. So we can perform this calculation by pressure enthalpy chart, as this one with the numbers on both axes, and for the isotherm as entropies and so on. Or I can go use the graphic operator manual, or I can use the GCAP to do the calculation. To save time, so let's do the GCAP. The input information is the same as before, except we have two stages of compression, so we have two efficiencies, which are kept the same. Pressure they're up the same. So the program calculated first stage compression, second stage compression, first stage power requirement 561.55, second stage 740. If I add these two power requirements, the sum would be 1,302 horsepower, and that compares much lower than 1,533 that we obtained for simple refrigeration system. Again, we see summary table later on to make the comparison. And look at the fraction of liquid. Fraction of liquid in the chiller is 82%. If you remember, it was 59%. Liquid now is 82%. And for the economizer, the fraction of liquid is 74%. So by doing this arrangement, with lower compression power requirement, normally it could be in the range of 15 to 25%, depending on the process. And this is the equation how to determine the interstage pressure. So chiller pressure or suction pressure first stage times the discharge pressure of second stage. Take the geometric average. That gives us 86 psi at the interstage pressure. If you don't have access to computer program, you can use the operator training manual of Petri skills course. So all I need is the chiller temperature, condensing temperature. We did similar for single stage simple refrigeration system. Again, I read the number here, 152 multiplied by 8.1 million BTU. This chiller duty, because this is million BTU per refrigeration duty, which is the chiller duty. Then I adjust for the efficiency. I get 1313, and GCAP got 1302. Very surprisingly, very, very close to each other. So handy tool for quick calculation of power requirement. It doesn't give, and this is based on the equal compression power, because I check it with high sys, how this, make sure how they generated the power requirement is the same. The power requirement for both stages are the same. And also, it was assumed the pressure drop is 5 psi in the condenser and discharge line to the compressor. So now I know the compressor duties. I know the chiller duty. So if I add them, I get the condenser duty as well. So condenser duty 11.44 and GCAP gave 11.42 million. Again, perfect match. Very good match. Very good match. So to summarize what we obtained, so base case, which was simple refrigeration system, for the objective of for the design chiller duty of 8.1 million BTU, chiller temperature minus 4 degrees Fahrenheit, which corresponds to 36 psi, a chiller pressure. We get the condenser duty 12 million for base case. If I use economizer, flash tank economizer with two-stage of compression 11.4. If I use cooled process gas available as my cooling media, 9.4. The pressure, condenser pressure for base case and economizer with the vessel is the same because they both use the same condensing temperature. What for the cooled process gas, cooling media, the temperature was 54, so the pressure is 101 degree, 101 psi. Mass flow rate, simple refrigeration system is 21.8. Here mass flow rate is 21 through the second stage, but through the first stage mass flow rate was 15.5 pound mass per second. What the mass flow rate was the smallest in the last column, which was for cooled process gas. Look at the power requirement. The simple refrigeration system has the highest, with the economizer with lots of capex and opex, 1302. If I use optimum, absolute optimum, it's based on geometric average interior stage pressure. This is based on equal compression power for two stages. And our favorite one is 723 horsepower for cooled process gas as a cooling media. By the way, this require extra capex, things like that. This guy no capex, no extra capex. The same equipment you can use, and it's more effective. But this may not always be available, the cooled process gas. So if no process gas, cooled process gas available, then instead of this, you go to the economizer with extra capex and opex. But you do a lot of saving on compressor side, both capex and opex as well. Percent of vapor into the chiller, 41% for simple refrigeration system, 19% with economizer. I put 20 in the parentheses for the economizer because in the mechanical refrigeration system, with flash tank economizer, we had two JT valves. So one of them for economizer, one of them for upper stream of the chiller. And the power reduction, or how it compare these two guys with the base case. So if I divide 1302 by 1533, I end up with 85% liquid. Sorry, the power requirement goes down to 80.5% of the base case. If I use this guy here, the power requirement would be only 40% of the base case. So this is the most effective one. This one, the most effective one. And I have similar table for the SI trends. So to summarize here, by going from simple refrigeration system to using simple refrigeration system, but instead of using air or water as a cooling media, I use a cool process gas. We get lots of saving, and the power reduction is drastic. Or if you go to mechanical refrigeration system with one flash tank and 2 stages of compression, again, we gain some saving on compression power requirement as well. Of course, the approach temperature play an important role as well. I better speed up a little bit. Here's the computer simulation algorithm I did for a case study for our G5 advanced application of computer and gas processing. I use Unisim. You can do that with Unisim, Promax, HISYS, any other software as well. I use adjust to change interstage pressure here in a way that the power requirement for first stage and second stage become equal. And the computer program automatically did. Here's how I define my chiller duty. And as you see here, the power requirement here is 7.93 kilowatt, 793 kilowatt, and interstage pressure is 471 kilopascal. So automatically determine the interstage pressure subject to equality of this power, and this gives a minimum total power requirement. And to show the effect, what I did here, effect of interstage pressure on compression power requirement, I plotted the total compression power in kilowatt versus interstage pressure. On the right-hand side is the compression ratio for each stage. The blue curve, variation of compression ratio for first stage. The red one is compression ratio for second stage. And the green is the total power requirement. So at this point, the compression ratio per stage are the same, but the power requirement is not minimum. The power requirement is minimum at this pressure here, at the minimum of this curve. If I go with this one, my interstage pressure would have been 350, almost 370. If I go with the total power requirement, the total power requirement is minimum at a pressure of what? 460 kilopascal. To make my case, similar diagram, power requirement for stage 1, for stage 2, and total power requirement. At this point, the power for each stage is the same. And if I continue here going to the total power requirement, my total power requirement is minimum. So this verifies that the total power requirement is minimum if the compression power for each stage are the same. But when we teach in classes, we say we can minimize power requirement if you go equal compression ratio. So why is not the case in this diagram here for our refrigeration system? Well, to make the statement correct and complete, I should say total power requirement become equal when compression ratio are the same if suction temperature for each stage is the same and mass flow rate through each stage are the same. But in our mechanical refrigeration with 2 stages of compression, the temperature to first stage was, say, -4 degrees Fahrenheit. The temperature to second stage is about 44 degrees Fahrenheit. And the mass flow rate in the first stage is about 15.5 pound mass per second. The mass flow through the second stage is 21 pound mass per second. So it doesn't meet the condition for equal compression ratio per stage. But the total power has become minimum if you just go with the equality of power requirement for each stage. The last item I'm going to share with you using heat exchanger economizer. And I did it. But by the way, this work I did as a tip of the month in December 2017, which is still posted in our website, Campbell website. And to study this one, I did another tip of the month, which on the next slide, I showed the summary of the result as well. So this is a simple refrigeration system. What we did, we added another heat exchanger here to exchange to do subcooling. So here we're coming out of the condenser, saturated liquid. We go to heat exchanger. We go to heat exchanger. We cool it down at the cost of raising the temperature of the cold gas out of the chiller. So what happened when we come through here, pressure goes down, so suction pressure, compressor goes down, and temperature goes up. But let's follow the path and then come back here. So I'm going in saturated liquid. When I'm coming out, I'm be at point A subcooled because I'm cooling down saturated liquid. Then I go to JT valve. So I have this fraction of vapor, which is good. My mass flow rate is going to be lower now. But when I come out, say saturated vapor, but this saturated vapor is going to get heated up, becomes superheated, as well as pressure goes down. So what I have through my compressor is superheated vapor at higher temperature, lower pressure, and lower max flow rate. Generally, the combination of this effect is higher power requirement. Some unique cases, the power requirement may go down, but we have to be very careful with if we want to use this kind of arrangement. We have to do some computer simulation, making sure the system works. On pH diagram, the cycle, the blue cycle is the original one without this heat exchanger, and the green one is with this heat exchanger. As you see here, the fraction of, originally the fraction of liquid was this much, but as a result of putting that exchanger and economizer in the middle, the fraction of liquid become from here to here. The fraction of liquid increases, the mass flow rate goes down, and fraction of vapor is low. But here, because the pressure drop, we go down because y-axis pressure and temperature shift to the right because temperature increases. So the net effect is the power requirement goes up compared to simple refrigeration system. To back up my claim, as I mentioned, I did a 2014 tip of the month. This is a summary of specification. The DUT is chiller temperature, condenser temperature, the pressure drop through the system, and then let's take a look at the result of computer simulation. This is the mass flow rate as a function of subcooling temperature. No subcooling, as the temperature was 35 degrees C, this condensing temperature, and it's saturated liquid. If you do subcooling, lower condensing, lowering the subcooling temperature to this low value, the mass flow rate goes down, which is favorable. Even though I have different pressure drop in the heat exchanger on the gas side, my mass flow rate goes down, which is favorable. This diagram showing the suction temperature, which is the suction temperature of the gas going to the compressor. As subcooling goes down, I get more superheated. So I'm starting from 35 degrees C, and my suction temperature, which was minus 35, now my suction temperature increased drastically to minus 14. So a good amount of temperature rise, which is not good for compressor. And also, as a result of that, what happened to my power goes up drastically. If there is no pressure drop in that heat exchanger on the gas side, that works perfect, but that would be in our dream only. But realistically, we have pressure drop, and the pressure drop causes the power requirement to go up much higher. Again, we have to be careful when you use this kind of arrangement. The only time may work that we use external source for subcooling. If you use external heat exchanger for subcooling, that works. If I have available some cooling gas or some liquid, I can use it as an external source. So we covered lots of material. Let's review the highlight of the item 1, a possible minimize process gas chilling duties such as use of gas or gas liquid exchanger upstream of your chiller. That reduces your duty requirement of the chiller by sometimes 60%, 70%. And also optimize the upstream heat exchanger temperature approach. Temperature approach has a big impact. Lower temperature approach, your heat exchanger duty goes up, capex on heat exchanger goes up, but duty of your chiller goes down drastically and you save a lot of money. So when you size the refrigeration system, don't look at the chiller itself. Have an eye on the upstream gas or gas liquid heat exchanger to lower the chiller duty right at the start. Item 2, if possible, use an available cold process stream as cooling medium to condense compressed refrigerant. As we did. You guys are going to receive a copy of this PDF, this presentation. So item number 3, use one or more flash tank economizer with 2 stages of compression, 1 or 2 or more. Sometimes we use more stage of compression. And also optimize the interstage pressure. And we talk about 2 different types of optimizing interstage pressure: equal compression ratio or equal compressor power per stage. And finally, we talked about use of heat exchanger economizer may increase power requirement. So if you use that, be aware of it. But if you use external heat exchanger, use the external source for subcooling, should always work. Couple of more takeaway from this presentation: decreasing the condensing temperature, decrease the compression power. Just emphasizing what we said before, but keep in mind too low condensing temperature and a centrifugal compressor may run into a stone wall. Your discharge pressure will be low, your mass flow rate may be high to get you to sonic velocity and reach stone wall. And too high condensing temperature and the compressor may hit its power limit. This may happen during summertime when condensing temperature increases. The second item, presence of light air increases condensing pressure. And if condensing pressure increases, that means compressor power goes up. And finally, presence of heavy component increases chiller temperature. And that you have to decrease your chiller pressure, and decreasing chiller pressure means more power requirement. And if you guys would like, let's do a Kahoot quiz. And here's some tips how to use the Kahoot. So please take your cell phone out, please, And in your browser, type kahoot.it, and I'm going to start the quiz and showing you the PIN number, so you can enter the PIN number and your nickname and so on. All right. Got 8 quick questions. Review our material to make sure we are on the same page. After the quiz, you're going to have Q&A as well. So here's the PIN number. I'm going to wait 1 more minute. I'm going to start, and you can join us if you want. Choose the best answer. All right. Majority got it right. We need all of the items listed to evaluate or size a refrigeration system. Very good. Roro is on top. And the number 2 and number 3, probably they all got it all right. But speed is very important. The faster you do, the more points you get. So we got two correct answers. Both, some cooling takes place in the condenser, and the remaining cooling takes place in the expansion valve. And majority got it right again. Thank you. Leonardo, excellent job. Awesome. Again, majority got it right. Thank you. If the score is low, sometimes it's my fault. Very good. Again, majority got it right. So we enter the chiller at low pressure. Condenser is highest discharge of compressor is highest pressure. Chiller has got the lowest pressure. And if one day we can get into a chiller 100% liquid, that would be, I think we became millionaire. Excellent, Leonardo. I think this is the best performance so far. Very good. We are getting better at the end. Thank you. So we had two minimization, one using equal compression ratio, which some of you selected, and the absolute one was the one that we had equal compression power per stage. So those who choose the red one, they get partial credit, but unfortunately, Kahoot does not allow that. But feel good if you choose the red one as well. Last one. Awesome. Thank you, guys. Congratulations.
All right. Good job, everybody. So we have a few minutes here at the end. Mahmoud, I've got a few questions here, so I will run through those with you. And then if anybody else has questions, feel free to go ahead and type them into the chat or the Q&A, and we will hit those at the end. All right. So first question here is, have you tried using a liquid expander instead of the JT valve?
I personally haven't, but I can ask some of our colleagues and get back to you later on.
Okay, very good. Next question is, when installing a subcooler in series with the condenser, how would it affect compressor power requirements?
It increases the power requirement, but not that much, because you are adding the delta P, so your discharge pressure would be a little higher, but not that much.
Okay. And then last question, what happens to the gas-gas heat exchanger and chiller duties if a minimum temperature approach is taken between inlet gas to gas-gas heat exchanger and residue gas?
Okay. The effective approach temperature is impacting increasing the heat duty of your gas-gas or gas-liquid heat exchanger. And because the total heat removal is constant, so if your gas-gas exchanger duty increases, the chiller duty goes down. So it's a good way of, lowering your power requirement, lowering the chiller duty through utilizing minimum approach temperature.
All right. Very good. So that's it for the questions. If anybody does have further questions, I'll be sending an email out with the recording of this presentation. So feel free to respond to that and let me know what questions you have. And we'll be including the various courses and online learning modules where you can find out more about these topics as well, in that you can see those up on your screen. So Mahmoud, thank you very much for an excellent and very informative presentation. We appreciate it.
Thank you, Clay, and thank you, everybody. It was a pleasure to deliver this webinar to you guys, and hopefully we meet in person someday, somewhere in the world.
Someday. All right. Thanks, everybody. Take care and stay safe.
Best wishes to all.
Yep. All right. Bye-bye.